but still, translators take what kind of code? Source code, and produce object code. Yes. So this whole process, the compilation process takes source code and produces object code, and it does that through these three stages. Remember, we looked at this right at the start of this presentation with assembly language, and the process of taking your assembly language and producing the machine code. This process is very similar. So you start with your source code. Right at the very top, you've got your source code. And it goes through lexical analysis, syntax analysis, code generation. By the time you get to the bottom, you've got your finished machine code. A common question on the exam is something like, describe the syntax analysis phase of, compilation. Or it'll be something, or it can equally ask about the lexical analysis or the code generation phase. Doesn't matter which of these three phases it's asking about, these same 3 marks always come up. So regardless of which stage they ask you about, you say, it takes the output from syntax, takes the output from lexical analysis, and produces the output for the code generation phase and gives errors. So if you're talking about syntax analysis, you say what happens, you say lexical happens before, code generation happens next, and gives errors. And if the question is asking about the lexical analysis stage, you say it takes the source code and gives output to the syntax analysis phase and gives errors. Regardless of which phase they ask about, you say what happens before, you say what happens after, and you say gives errors. 3 nice easy marks. This same question seems to come up quite a lot. They just change X depending on which phase they're asking about, obviously. But this almost exactly the question comes up quite a bit, and that's 3 marks, and the question is usually out of 5. So you need to remember another 2. So there are these 3 stages: lexical analysis, syntax analysis, and code generation. And you need to know a fair bit about each one. So, given that we've already talked about assembly language and the process of turning assembly language into machine code, lexical analysis takes the source code as its input. And it has to change that source code in some way to sort of make it easier to process later on. So what kind of things do you think it needs to do? Any ideas? You've got your source code, which is your human readable form of the language. What kind of things is it going to have to do? Any ideas? No? Comments, yes, good. Definitely. One of the first things it has to do is get rid of the comments. Computer doesn't need them. Why would the computer be interested in your comments? So yes, definitely. One of the first things that happens during lexical analysis, comments are stripped out. Any others? Anything else? As well as removing the comments, what else is in there just to ease readability? Spaces. Yeah, good, excellent. So yes, lexical analysis takes the source code, removes the comments and the spaces. These aren't really necessary for the later process. Good. Let you go a bit longer and see if you got the next bit. So create tokens for reserved words. So maybe a bit less logical, although it does make perfect sense. I'll let you write that down. And gives errors, obviously. Yeah, good. Takes the source code, removes spaces and carries returns and white space, removes comments. All that stuff makes it easier for humans to read. But once it's done that, it can create tokens for return work. reserved word is one of the words of the programming language, one of the words or symbols that are expected by the programming language. Words like for and while and public static void main, those sorts of words. Those are reserved words. Those are words that are used by the programming language, reserved for the use of the programming language. You can use them yourself to an extent, I suppose. You can create a variable called public, probably. I've not tried, but I imagine I'll let you. Interesting to know if you can create an int called int. I suspect you probably can, because the programming language can work out from the order of the words. Nevertheless, that does make it slightly more tricky for the compiler. The reserved words of the programming language are turned into tokens. This is similar to an assembly language where the mnemonics are turned into machine code. The tokens aren't quite machine code, but they are more machine readable than the reserved words. So it's an instruction, basically. It's taking those reserved words and turning it into a sort of instruction equivalent, something similar to an instruction. The reason it does that is because during the next stage, it checks syntax analysis is checking the rules of the language. So all those other marks apply, it gives errors, it takes the output from the lexical analysis stage, and gives its output to the code generation stage. But the extra thing about syntax analysis is checking that what you've written meets the rules of the language. And the way it does that is by looking at the order of the tokens. By looking at the code you've given it, and the tokens that it's then turned it into. If you've written public static void, it knows that the next token it should expect should represent main. If it represents a closed bracket, it knows it's got a problem. Similarly, if you write for, it knows what to expect next. If you write if, it knows to expect some sort of Boolean expression next. If it doesn't get a Boolean expression, or an open bracket with a Boolean expression inside it, it complains and throws out a syntax error. It's broken the rules of the language. So that's what tokens are, and that's how they work, and that's what syntax analysis is. Any questions? Finally, we have code generation. Well, the first one is pretty obvious. What does code generation do? Reduces code? Code generation reduces machine code. But the crucial difference between code generation for a high-level language and used by a compiler and code generation in an assembler is that an assembler, in a low-level language, one instruction in machine code, or one instruction in assembly language is one instruction in machine code. But in a high-level language, one high-level language instruction can end up being several low-level language instructions. Several human instructions can be multiple machine instructions. And the last thing it does is all those lovely variables and functions that you diligently use inside the structural code are given addresses. Probably relative addresses. Certainly more likely to be relative than direct. Because direct addressing you can only ever run in that space in memory. Whereas relative addressing, you've got programs that can share the memory with other programs. And the last phase of this, remember one of the big advantages of compilers, well there are three advantages: hides the code, checks for errors. What's the other big advantage? Optimization. What is optimization? How do you think the code could be optimized? Reducing the size, yeah. I mean, if you look at the code, it's basically a bunch of instructions. All you're doing, optimization is reducing the number of instructions in the method. Reducing the decode, sorry. Which does what? Remember, be stupidly specific, statement obvious. What's the purpose of optimizing your code? Makes it faster. Yes. Good. How does it make it faster? By reducing the number of instructions, which makes it more good, man. Good work. So optimization makes your code as efficient as possible by reducing the number of instructions. And this improves the speed of your program. Makes your program faster. At this stage, you might like to tackle some of the questions on the worksheet. And then I'll fill you in with the last section on this topic, which is libraries.